Welcome to the Deep Dive. Today we're plunging into a really fascinating challenge at the cutting edge of quantum computing. We've been digging into a recent paper from Classiq Technologies. It's dated June 10th, 2025, and it's called Efficient Quantum Control via Automatic Control Skips. So our mission for you today is to unpack how this, clever new approach is making quantum programs much more efficient. It's doing this by finding these shortcuts that were maybe hidden before or just required a lot of painstaking manual work.
Indeed. We're really looking at how to make these crucial quantum operations less expensive and, more effective overall. It's fundamentally about making quantum computation more practical, more powerful. And this paper offers a really direct path to understanding one of the core challenges, and I think a surprisingly elegant solution.
Okay, so let's unpack that a bit.
Yeah.
When we talk about quantum control, what exactly are we referring to? I mean, in classical programming, we use conditional statements, those if-then things, all the time. Is quantum control basically the same idea?
It is. It's the quantum equivalent, precisely. However, classically, you evaluate a condition, a Boolean condition, just by measuring it, right? But in quantum computing, measuring a qubit collapses its wave function.
Okay.
It destroys that coherence you absolutely need for the computation. So it's highly discouraged, a big no-go, really. Instead, we use something called unitary controlled operations. These manage to preserve that crucial coherence.
Okay, so these controlled operations, they keep the sort of quantum magic alive, but you mentioned they come with a significant overhead. What does that actually mean for the circuit? What's the cost?
It means higher costs, yeah. In terms of resources, a simple example. A single qubit control on a single qubit jade. That turns it into a two-qubit gate.
Right.
And two-qubit gates are just inherently more error-prone. They take longer to run on pretty much any quantum computer hardware out there. Plus, if you need multiple controls, these multi-controlled gates, they aren't typically implemented natively. You have to break them down, decompose them into sequences of single and two-qubit gates, more cost, more errors.
And I imagine that cascades, especially with things like error correction.
Exactly. The paper mentions the particularly costly T-gates, which are often vital for fault tolerance. Controlling those adds significantly to the overhead. And given how, scarce quantum computational resources are right now, efficiency isn't just nice to have, it's absolutely paramount.
Okay, so the cost is clear. This is where the paper introduces this really brilliant idea, skipping controls. The paper says it is often possible to skip the control of some operations, which greatly improves circuit quality. How does that actually work? How do they find these skips?
Well, the most prominent way they discuss is by identifying what are called conjugation pairs.
Conjugation pairs, okay.
Mathematically, it looks like U dagger VU. Basically, you can think of it like this. You perform some intermediate steps, that's U. Then you do the operation you actually care about, V. And then you undo the intermediate steps with U dagger.
To clean things up.
Exactly, to release resources or return qubits to their original state. And the neat trick is the control on that central operation, V, effectively becomes active only within that U dagger U sandwich. And these patterns, they're described as ubiquitous in quantum algorithms.
Why so common?
It comes down to the reversible nature of unitary computation. You often need to compute something, use it, and then uncompute it. A good example they give is ripple carry addition. It can be implemented just as a sequence of these nested conjugations.
That's clever, using the uncomputing step to enable a skip. Are there other types of skippable patterns, though, beyond just these conjugation pairs?
Yes, there are. Conjugation pairs are actually, you could say, a special case of a broader property. The general idea is if you have a sequence of operations and some subset of those operations, when you multiply their effects together, results in the identity operation.
Meaning they cancel each other out.
Precisely. They effectively do nothing as a group. Then, the control applied to that whole subset can often be skipped. The paper shows an example, I think it's figure 1, from algorithms using gray codes. There, you have 4 CX gates, and it turns out the control in all 4 can be skipped because their combined effect is identity.
Okay. Identifying these sets sounds incredibly powerful. But as the paper notes, it also sounds really, really hard. It says the search space is immense, since there are exponentially many operation subsets. Why is finding these manually just not practical?
That's exactly the challenge. I mean, you might spot some obvious ones from a high-level view, right? Like the compute-uncompute conjugation pairs. You can see the functional intent there. But you could easily miss others. For instance, maybe deep in the circuit, an X gate happens to be applied twice to the same qubit.
X squared equals identity.
Right. So that could be skipped. But you'd only see that if you looked at the very low-level gate description. And the problem is, scalable quantum programming requires a high-level description. Nobody wants to manually optimize thousands or millions of individual gates. It's just impractical.
Which brings us to the really interesting part, automation. This paper reports on a generic method for automatically identifying possible skippable subsets. What does this automation actually bring to the table?
Well, it means moving beyond these manual, often algorithm-specific tricks. They formalize the problem, calling it the max conjugation pairs, or MCP problem, although the method applies more broadly. The core idea is to find the best set of skips. They assign weights to potential skips based on how much benefit you'd get, how much cost you'd save.
Because not all skips are equal.
Not at all, and there's a crucial rule for a set of skips to be valid. The operations within the chosen skip pairs must either commute, meaning their order doesn't matter, or their sections in the circuit sequence just can't overlap. This constraint makes it relatively simple to verify if a proposed set of skips is actually valid.
That makes sense. And we give an example, right, with X and CX gates.
Yeah, they show a case with interlacing pairs, like X on one qubit and a CX involving that qubit. Skipping the control on the CX gate is much better.
Why is that?
Because if you did control that CX, it would become a CCX gate, a Toffoli gate. And those are complex. They typically decompose into at least 3 CX gates, maybe more, depending on connectivity. So skipping the CX control avoids that big cost increase.
Got it. But then the paper drops this bomb. Finding optimal subsets is generally NP hard.
Uh-oh.
For you listening, what does NP hard really mean here? Is it game over?
Not quite game over, but it means it's computationally very difficult. Seriously hard. There's no known algorithm that can efficiently find the absolute, provably best set of skips for any possible circuit, especially as they get large. They actually proved this formally by showing it's equivalent to reducing it to another famous hard problem called the max-weighted independent set, or MWIS problem.
Okay, a known beast in computer science.
Exactly. Think of MWIS like trying to pick the highest value committee members, but certain pairs just refuse to work together. Finding the perfect committee that maximizes value while respecting constraints is NP hard. Same idea here with skips.
So, okay, if finding the optimal solution is basically intractable for large problems, how on earth do they get these results they report, like over 50% improvement? Are they just getting lucky?
No, not luck. This is where approximation algorithms come in. Nevertheless, as the paper says, suboptimal polynomial approximation algorithms can still provide significant improvements. You might not find the absolute perfect set of skips, but you can find a really good one, and you can find it reasonably quickly in polynomial time.
Okay.
And because their MCP problem is reducible to MWIS, they can actually adapt existing successful approximation algorithms designed for MWIS. The paper describes one specific approach they use, a dynamic programming algorithm. Now, this algorithm makes a simplifying assumption to make the problem tractable. It assumes that no operations commute.
But wait, you said operations commuting is important and operations on different qubits do commute.
Exactly. That assumption is implausible in real-world circuits, as the paper admits. Operations on different qubits do commute. But here's the clever part. Even though the algorithm finds the solution based on that simplified, less realistic premise, the solution it outputs is still guaranteed to be a valid set of skips for the real circuit. It might not be the absolute theoretical best, but it's valid and, as the results show, often very effective.
Fascinating. So what kind of real-world improvements did they actually see with this generic automated approach in their experiments?
The results are quite impressive, especially considering the method doesn't need to know anything specific about the algorithm's purpose. For what they call random brickwork circuits, these are sort of generic test circuits, they saw gate counts and circuit depth reduced by about 8%, which is okay, not bad.
Decent.
But for state preparation circuits, and these are really important, used in many algorithms to set up the initial quantum state, the reduction was over 50%.
Wow, over 50%. That's huge.
It really is. And the key takeaway is that these significant gains are achieved even without knowledge of the intricate details of each algorithm. It's a truly generic optimization.
So, stepping back, what does this mean for the field? Does this kind of automatic optimization make all that careful, specialized work people do designing specific quantum algorithms less important? Are compilers going to take over?
Not at all. I wouldn't say obsolete. The paper is quite clear. This automatic control skipping method will probably not outperform specialized implementations. Think of it more like an additional layer of optimization. You'd still want the clever human-designed algorithm as your starting point. But then this method could be used on top of that specialized implementation to find further savings.
Like a compiler optimization pass.
Exactly. It fits perfectly within the framework of a quantum program compiler. Just like classical compilers apply optimizations like loop unrolling or constant folding without the programmer having to tell them exactly how. This method is blind to functional intent. It doesn't need to understand why the circuit does what it does, and it requires no effort from the programmer. That's its real power.
It really sounds like it's tackling that scalability problem head on, making it easier to build and run larger quantum programs.
Precisely, that's the key implication. As quantum programs increase in size and complexity, generic optimization methods prove more useful and are key to implementation at scale. The paper also makes an interesting point about decomposition. How you initially break down complex gates into simpler ones can really impact how successful these skipping algorithms are.
How so?
Well, they give an example. If you have a sequence like XZH, you might not see a skip. But if you rewrite the ZH part using Hadamard gaze as HXH, so the sequence becomes XHXH, suddenly you might have an XHX structure which could reveal a hidden conjugation pair, H dagger equals H.
So the way you represent the circuit initially can hide or reveal these optimization opportunities.
Exactly. It's like, sometimes tidying up your desk reveals shortcuts you didn't see before. Same idea for quantum circuits. The representation matters. What's really fascinating to me here is how this abstract realm of quantum operations, qubits and unitaries, benefits so much from these very practical, almost engineering-like automated approaches. It's about hiding complexity, making the underlying knowledge actionable and the systems efficient, even when finding the absolute perfect mathematical solution is, well, impossible or impractical.
Yeah, it really bridges theory and practice. And imagine, for you listening, the impact when quantum compilers can routinely find and apply these kinds of optimizations. Optimizations that humans might easily miss or just find far too tedious to search for manually across massive circuits. It could dramatically speed up development and make quantum computations faster, more reliable. It really lowers the barrier for creating complex quantum software. So the question it leaves us with is, what new possibilities does that truly unlock for the future of quantum applications and for computing itself? That's something worth pondering.